Hello, this lesson will be about the second derivative, and this honestly is when things usually start to get a little bit murky. Calculus kind of starts playing with your head a little bit here. The first derivative is probably pretty simple when you thought like when the first derivative is negative, the function's heading down, and when the first derivative becomes positive, function begins heading back up. I think that's pretty intuitive, just based on, again, the old idea of tangent slope this way, function heading downhill. Tangent slope this way, function heading uphill. And this is always, of course, interpreted from left to right. Well, the second derivative deals with something called concavity. When something is concave up, it looks like that. When something is concave down, it looks like that. And it can be any part of this. So this one's up, think U up. And this one's concave down. So it could also be, just that would be concave up, or just that would be concave up, or even that part of it is concave up. So it's anything that generally follows that shape is concave up, and anything generally follows that shape is concave down. And you might be thinking, what the heck do we care about U shapes or upside down U shapes? Who cares? Well, the basic deal with concavity is something is concave up if, and this is where things get really weird, if the derivative of the graph is increasing. The derivative is increasing, not the function. So you can't look at the function. You have to think about it's either its derivative graph or simply the numerical value or the look of its derivative. So in this particular function, the derivative is increasing the whole time. As you start from here and go to here, the derivative increases as you go. Versus this one, the derivative here to here, the derivative is always decreasing. Now, the derivative was based on when the function was increasing or decreasing. So we're effectively saying here, it's concave up if the increase is increasing. And it's concave down if the increase is decreasing. Which sounds sort of crazy. There's a couple ways of looking at this. First, the good old tangent ruler method helps. So, think about what its derivative is there. Looks to me like maybe negative 15, just based on its slope, if I'm assuming a square coordinate plane behind my graph. So it's negative 15. Now what is it? Maybe negative 10. Maybe negative 1. Maybe negative a half. 0. Think about those numbers. Negative 15, negative 10, negative 1, negative 1/2. They're all getting bigger. Remember, going from left to right on the number line means getting bigger. And then you hit 0, and then it's 1. Then it's 2. Then it's 10, whatever. So from here, it's a very large negative number. It becomes less and less negative. In other words, it's increasing till it hits 0, and then it becomes positive. Whereas on this graph, it starts out extremely positive. Less positive, less positive, less positive, less positive, 0. Now slightly negative. More negative. More negative still, until it's extremely negative here. So this one went from a very high value to a very low value, and this one went from a very low value to a very high value. There are some very useful interpretations of this as well. 1 second. Hey, can I call you back on recording? Okay, bye. Sorry about that, phone call. So, yeah, those are the general pictures of concave up and down. Now, if you're trying to determine when the function increases or decreases, you simply take its derivative, because the derivative tells you how much it's changing. Well, now our problem is, we want to know when the derivative itself is increasing or decreasing, So what we're going to do is the same exact thing, take yet another derivative and look at that thing and say, if it's positive, then the derivative must have been increasing. Therefore, the function's concave up at that place. If the second derivative is negative, then that means the derivative must have been going down, which means the original function is going to be concave down there. So it doesn't mean the first derivative was negative there, it just means the first derivative was heading down, right? So the test for concavity is, we're going to say it's concave up if f double prime of x is greater than 0. So this is concave up, it's concave, C-O-N-C, concave down if f double prime of x is less than 0. Okay. And there are some very useful interpretations of this if you're thinking, well, how long are we going to go on with this? You know, are we going to keep doing more and more derivatives? No. So let's take the function on that PDF again. There's a different, I posted a PDF relating to this one. Negative x cubed plus 3x squared minus 2. Now we'll take the derivative of that. Negative 3x squared plus 6x. This would be the kind of place where you would pause and do it yourself. Now, again, take the derivative of the derivative, also known as the second derivative. Notice the derivative to 0. And you get negative 6x plus 6. And now, if we want to find when that thing is positive or negative, because it'll tell us about whether or not the derivative is increasing or decreasing, which will tell us about concavity, we need to set it equal to 0 and solve, and you'd find 1 in this case. So now, I'm just going to make a little line here. Testing values in the derivative, for example, 0, you'd get positive 6. Okay, that's positive. And then if you test a larger number in here, number larger than 1, you'd find it's negative. Which means our function is concave up from negative infinity to 1. And it's concave down from 1 to infinity. So type this little guy into your calculator. Negative x to the third plus 3x squared minus 2. And you're going to see a concave up portion on the left side, so this kind of shape, and then this kind of shape. But of course, they're not just going to be disparate like that. Somehow they'll kind of unite, and if you see your graph, will kind of look like that, where 1 is somewhere in here. Right? It's concave down, then, it's concave up, and it's concave down. By the way, if you were to have studied the derivative, if you were to have set the derivative equal to 0 and solved it, notice the derivative is quadratic. You would have found 2 places where the function changes from decreasing to increasing, decreasing to increasing. So this little green spot right here would have been a critical value on the first derivative, and also that green spot would have been a critical value on the first derivative. So the first derivative will not tell you the same information as the second derivative. Remember, the first derivative is there to tell you when the function increases or decreases. The second derivative tells you about the concavity. We called these values relative mins and relative maximums, the 2 green values. We're going to define, and I know I'm jumping a little bit ahead there, but I'll allow you to do some of those other functions. This black point, where it changes concavity, that's going to be defined as a point of inflection. So a point of inflection is a point where the concavity changes from upward to downward or downward to upward. And I think on the page I probably put upward to downward, but same deal, if it were to have changed downward to upward or upward to downward, whatever, it's still a point of inflection. So in the first derivative, we called them critical values, or we learned that a lot of times they were relative extreme values. In the second derivative, when it's still clearly increasing that whole time from the green dot to the green dot, it's clearly increasing. This black point is of interest because the function begins to change in concavity, or does change in concavity there. I want to talk very briefly, and I'll leave a lot of the other examples to you to do, but I want to talk about what a change in concavity means. And I'll talk about that in the context of you studying for a test. I think this is generally the picture of, if this is time studying, and this is grade on an assessment. Generally, if you put very little time into studying, you're going to get very little result. But after maybe about 10 or 15 minutes into a certain course, if you've studied for maybe, I don't know, let's say 20, for a quiz, let's say. It's a quiz on a couple chapters in your IB English class. The first 10 minutes, you're not going to get very much out of it. You're kind of getting yourself reacquainted with the chapter. And then, you know, between 10 and 20 minutes, it's like, okay, now I know what I'm doing. I remember what happened in this chapter. That was a very productive 10 minutes. Now, you go to your next 10 minutes, from 20 minutes to 30 minutes, and you're about here somewhere. You've picked up a lot between 10 and 30 minutes. Every minute there was more and more helpful than the minute even before it. But then after about 30 minutes, you've kind of done a lot of what you should have done already. And the 40th minute, between 30 and 40, yeah, it'll help. But notice the help between 20 and 30 was on an upswing. Look at the curvature of my hand. Versus here. Concave up, concave down. So what's happened here is you are increasing. Every minute you study, you're probably slightly increasing your performance or your grade. But if you get all the way out to the edge here, at like 60 or 50 or whatever, from the 40th to the 50th minutes, those are not as productive. Right? It's not doing this anymore. It's kind of flattening out. Which means the increase is increasing here. Slight increase, whoa, big increase, big increase. Now the increase begins to taper back off. This is called a law of diminishing returns. This will happen in economics all over the place. It happens in almost everything you do, even things from exercise to time spent studying to just, I mean, almost anything in the world. Of course, if you spend a little bit of time doing something, you get a little bit of an output. You spend more and you see a huge change. And then you keep practicing that violin for another hour after you've already done 5 hours. It's not that big of a difference compared to the difference you made in that first hour of practice. So that's just a brief lesson on why concavity is actually a relatively important thing for we human beings to study. So you can see there's a picture, x to the fourth. I'm on, I think, the third or fourth page in that document. X to the fourth minus 2x cubed. You can clearly see where inflection and concavity is there, but you can do that graphically. The last one on that page shows you a little bit of a logic trap with x to the fourth. You will see the concavity stay the same. Well, I don't want to reveal too much about it, but x to the fourth plays a little bit of a trick with you about points of inflection. So definitely look at that one. And then the second derivative test also. Okay, let's talk about that. In the second derivative test, if I know, for example, if f prime of 5 is 0, I'm on the last page there now, and f double prime of 5 is 17. If I were to make a picture of that graph, here's what I know about the graph. F prime of 5 is 0. Well, somewhere, 1, 2, 3, 4, 5, this function is either doing this, this, or this. It's one of those three options, right? Something in those three. But f double prime of 5 is 17, which tells me, it's concave up. Oh, must be that one. right? So this would be a sensible picture for these two pieces of information, which tells me the following. If the first derivative is 0 and the second derivative is positive, more important than 17, it's positive, then that's going to be concave up, which means that point right there must be a relative minimum. If the first derivative is 0 and the second derivative is negative, that must be a point like that, which means we've got a relative maximum. And if the first derivative is 0 and the second derivative is 0, then you've got some more information that you need to deal with in order to determine anything of the sort here. So you can find the relative extreme of those last values, and I hope this was a good lesson about why second derivatives can be useful and abstractly, how do we use them. Thank you.